Hi there, this is your moderator, Lori Dearman with WebAttract, your end-to-end solution provider for webinar demand creation. And you are in the right place for solving problems that matter, critical insights for preparing the next generation of engineers. And in just a moment, I'll be introducing our thought leader, as today's webinar is about hearing from this expert, as he discusses how institutional leaders, educators, and other key influencers can prepare the next generation of engineering problem solvers. Today we have a diverse audience of professionals from over 66 different countries and 35 states and provinces representing a variety of industries. Regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, the host of today's webinar is Elsevier, and before we get started, I'd like to turn it over to Humberto Bastos, VP of Engineering Solutions at Elsevier, who'll take just a minute of your time to officially welcome you and express what he hopes you'll get out of today. Humberto?
Thanks for introduction, Lori, and welcome everyone. I'm very excited that Elsevier is hosting today's session. We are very passionate about this topic, and for those new to us, we are an information business serving scientists, engineers, and researchers through products that apply technology and analytics to trustworthy content. Our mission is about helping people like you do the important work that you do. Whether you're educating future engineers, driving business forward, contributing to social progress, or working to enhance life and health for your communities. For the engineering field, we offer two solutions that maybe you already heard of, or perhaps you already use. Knovel helps users build applied engineering expertise and solve practical design and develop problems by providing best practice insights, equations, materials, and chemical properties data. Engineering Village is a comprehensive platform comprised of 12 engineering databases which provide academic engineering professionals and government users access to peer-reviewed, high-quality engineering research content in a single, very easy-to-use interface. Today's webinar focuses on what it means to be an engineer in today's world, where society's challenges continue to grow and become more complex. And as technology evolves, it is important to understand how expectations have changed and what educators and other key influence in societies can do to prepare the next generation of people that will help solve these important problems, big and small. So keep this in mind. Let me say welcome again, and I hope that you walk away from today's session with some insights, some new insights that you can use for your work. Thanks for joining us, and back to you, Lori.
Well, thank you so much, Humberto, for that warm welcome. And folks, speaking today, we have Dr. Lawrence Jones. I'd like to, if you would allow me a few moments and a few words in the way of an introduction. Dr. Jones, polymath, visionary thought leader, energy technologist, practitioner and futurist, social entrepreneur, and prolific speaker. Dr. Jones is an advocate for the use of smart, clean, and renewable energy technologies enabled by resilient infrastructures around the world. He is frequently an invited speaker at industry conferences and academic symposia for diverse audiences across the globe. He's published and been cited in scholarly journals, trade magazines, and newspapers, and also appeared on TV and radio internationally. He is a recipient of several awards and is recently appointed Vice President International Programs at Edison Electric Institute and is the co-founder of the Center for Sustainable Development in Africa. Today, Dr. Jones will discuss how institutional leaders, educators, and other key influencers can prepare the next generation of engineering problem solvers. So, a warm welcome to the webinar today, Dr. Jones. It's a pleasure to have you with us.
Thank you, Lori, and good evening or good morning, wherever you are. Thanks again for being here, and I absolutely would like to first of all express my gratitude to Elsevier and WebAttract for working together to put this webinar on. And really, I look forward to our engagement today and getting your insights, your questions, and also being able to just have a very good dialogue here over the next hour. So, first of all, just as a disclaimer here, I'd like to say that the views I'm about to express, the content and the views I will be expressing in this presentation are mine and do not necessarily reflect those of any organizations with which I am affiliated. Now, to set things off, let's begin with a very simple question, or let me just give you a scenario I'd like for you to consider. Imagine a day in your life in the year 2020, 2030, or 2050. And just try to imagine the kinds of challenges and problems you will have to resolve as you go through your daily living in the next 10 years, 20 years, 30 years. And the question to ask is, how are you going to solve those problems? Who will solve those problems for you? How are you going to get through your day in the next 20 years or 30 years by tackling some of the challenges you expect to face in the next decade or so? So keep that in mind through the presentation today, because I think it's very important, and you'll see the, the context from which this is coming from. One thing that is certain is that as we go forward, look into the future, everything is going to get smarter. The real challenge is, as things become smarter, do we become dumber in terms of how we engage with the physical world, how we engage with the systems that we design? And so as you look into the situation of who's going to solve the problems you will encounter into the future, obviously what comes to mind is that they will be solved by engineers. And engineering obviously becomes something that we see as one solution to solving these problems. So before we go further, let me ask Laura to do a quick poll so that we can all be on the same page in terms of what we consider to be engineering. And so, Laurie, can you run the poll, please?
I'd be happy to. Folks, coming up on this screen is that first poll, and we would like to hear from you. What is engineering? Is it a science, an art, both, or none of the above? All right, we have 22% saying science, 0 saying art, 72% both, 6% none of the above. What are your thoughts on this one, Dr. Jones?
Well, interestingly enough, I'm a bit disappointed that 0% said art. And I say that because I view engineering as being both a science and an art. Well, pleasing enough was that 72% did say it was both science and art. So I think it's very fair to see that the perception of engineering as being science and art is actually something that most people are beginning to accept. And obviously that's something I want us to bear in mind. And so we can continue on with the slideshow here. However, before we move forward, just want to make a point and really thank all of you on the call who actually send ideas on what you would like to learn from this webinar. We have actually read those questions or those ideas in trying to put together what we're going to do here today and discuss with you. And obviously, we will not be able to address every specific item that was brought up in the what you would like to learn, but we hope that the grouping of these ideas around big themes and key themes will help you to get some insights in how you go about addressing some of your own challenges as it relates to engineering and the education of the next generation of engineers. Now, if we continue on this, this is one slide, perhaps the busiest slide in terms of text, and I'd like to share with you because definitions matter. And this is a definition from Mojaran and Jung that I like because it's very all-encompassing. It defines engineering as a field of discipline, practice, profession, and art that relates to the development, acquisition, and application of technical, scientific, and mathematical knowledge about the understanding, design, development, invention, innovation, and use of materials, machines, structures, systems, and processes for specific purposes. A very long definition, but what is important is that you see from this definition how complex engineering as a profession is in terms of the many different facets that it has as you move in terms of understanding how you develop engineers for the future. You have to sort of look at this whole field from so many different angles. Now, as we talk about what engineering is, the next question is, let's step back and ask ourselves, what did engineers do in the past? What do they do today, and what will they do tomorrow? And I think this is very important because as we started off and looking into the year 2020, 2030, 2050, engineers are going to be solving problems to address your needs as individuals or needs collectively as a society. And so going forward, as we look at redefining or redesigning how we prepare these engineers, it's important to understand what will they be doing tomorrow. And in that context, as we look at what will they be doing tomorrow, we have to realize that engineering has evolved over time. Going back to the Stone Age and the other ages we've seen that design of solutions to problems facing man has evolved along three axes. One is scale, one is complexity, and other is speed. And most of what we'll talk about today somehow ties into these three dimensions: scale, the complexity of the solutions that we are putting in place today to address the problems, and speed, the fact that they're done at a much faster pace today. All of this has implications, obviously, for what we design, but I think from an educational standpoint, it's very important to understand these three dimensions as we go forward. Now, obviously, engineers build things. They build things that are big, they build things that are small, they build things that are simple, they build things that are complex. These things are built to solve problems, as we've already said, and sometimes these problems, you may consider them to be irrelevant depending on what it is that is being built, but at the end of the day, engineers are all about building things to address problems, and sometimes they build things way too big, sometimes they make them very small, but at the end of the day, engineering is all about solving problems and building things to solve those problems. Now the problem is, or the challenge here is, that these problems are constantly evolving, right? So the problems that mattered 50 years ago, today don't matter. The problems that will matter 50 years from now will be completely different from the problems that matter today. What is important as we go forward is to understand the evolution of the problem space in order to be able to design solutions, and also to prepare engineers to design solutions for dealing with those problems, which will constantly be evolving as we go forward. Now, the problems that matter today, like I said, some of them may matter tomorrow because of the complexity and just the scale of solving those problems. They will not go away over time, or not easily. So we have big problems like energy poverty, we have water poverty in the world, we have the problem of feeding 10 billion people, we have emerging problems like cybersecurity. These are all real grand scale problems that are being addressed. What is very important to emphasize here is that this attempt to understand how we train engineers for the future is something that is being addressed around the world. Many academic institutions, as well as research laboratories and governments around the world, are looking into this issue of how do you prepare engineers for the future. As a matter of fact, the United States National Academy of Engineering, in their attempt to try to address this issue of how you prepare engineers for the future, came up with 14 grand challenges. And these grand challenges range from everything as it relates to advanced personalized learning, advanced health informatics, designing medicine better, securing cyberspace, how do you design tools for advanced scientific discovery, how do you reverse engineer the brain, providing energy from fusion, how do you design and improve our urban infrastructure, and as well as how do you make solar energy more economical. Now, every country in the world, or every scientific institution, may come up with different types of grand challenges. My point with this is that these challenges will continuously evolve, and these are challenges that we need to be aware of as we go forward. There is another angle to this idea of preparing engineers that I think we need to think about, and that is some of the problems we are coping with today and will cope with in the future are classified as wicked problems. And they were classified as wicked problems simply because, first of all, they're very difficult. Oftentimes they're impossible to solve. They're incomplete problems. The definitions are sometimes contradictory. The requirements are constantly changing. And so how do you address such a problem in the world as we go forward is something engineers will have to cope with. We have examples like climate change, extreme poverty, predicting extreme events, managing urbanization. These are all examples of wicked problems, and these problems are on the rise. And so I think we need to be very clear as we go forward. So again, wicked problems, global energy poverty. If you look at the next slide that shows the world at night, you ask yourself the question. Today we have 1.2 to 2 billion people in the world who have no access to electricity. How do you provide electricity for those people in a way that is sustainable? And what does that mean for the environment? What does that mean for the planet in order to deal with providing energy in a way that doesn't harm the planet but that secures the future? So we have to deal with these kinds of complex energy-related issues. Obviously, urbanization is a big issue in a lot of cities around the world. Cybersecurity, population growth, all of these things are to some extent wicked problems because they're not easily resolved, and oftentimes they involve multidisciplinary approaches to come up with solutions. And engineers, although may not provide the complete solution for these very wicked problems, the incremental efforts of engineers can nudge the solutions along to end up having much better ways to approach how you deal with these problems. And lastly, I think coming back to the issue of global climate change, we have rising sea levels, we have greater floods occurring, low-lying cities that have to be redesigned, that have to be beefed up to withstand all kinds of extreme weather events. So resilience becomes an issue. We have severe droughts occurring around the world. All of these things, all of these problems are very multidisciplinary in their nature and also multifaceted. So, these are some of the challenges and problems that engineers have to be prepared to resolve as we move forward in this era of our time.
Now, Dr. Jones, given all of these problems that you've presented, how are we going to solve these problems and what we're calling grand challenges? What trends do you see affecting engineering and, of course, those teaching our engineers?
Excellent question. I think, one of the things we need to bear in mind is that with all of these grand challenges, we are fortunate as a people in this world that there are solutions on the horizon. There are a lot of technological trends that will allow us to have breakthrough solutions to address some of these problems. And let me just give you a couple of examples on some of these. First, obviously, looking at these trends is manufacturing, because a lot of things engineers do is to build stuff, right? So one trend we see coming in terms of manufacturing is the age of 3D printing. And 3D printing is going to really revolutionize how we go about designing things. Engineers build stuff, right? So obviously, with 3D printing, you can now prototype very quickly your ideas and get it to the market very quick, as rapidly as you would love to do that. Automobiles will be designed using 3D printing, machines and generators and other types of solutions will be designed using 3D printing. One of the beauties of 3D printing is that it takes manufacturing to a whole different level, right? So that's one thing we need to pay attention to, the impact of 3D printing. The other thing that I think is going to really help us address these challenges is the fact that much of the transformation of engineering as we know it have been driven by the advances in material science, right? So we know back in the day, going back to the Stone Age, as we started to use, different types of metals in terms of how we build our infrastructure. We now are beginning to see much more advanced metals like, graphite and silicon carbide. Interestingly enough, we could say that we're exiting the age of silicon. We're entering an age of new types of devices that would have all kinds of properties that allow you to design infrastructures that will themselves behave in ways that we cannot even imagine, right? So some of these grand challenges, whether it has to do with water poverty, energy poverty, urban reconstruction, material science is going to definitely allow us to have solutions to address some of these problems. Now, two interesting trends that are very important to bear in mind. One is what I call hyper-integration, and the other is convergence. Hyper-integration, because as you look at urbanization, you look at cities that will be built in the next couple of decades, right? You will see a kind of coming together of multiple systems. So you have the electrical systems, you have the water system, you have the transportation system. All of these systems are coming together. Most of them will be enabled by digital technology, by the way, which means we'll be integrating many different systems to provide solutions to all kinds of problems in cities. Transportation, we have more solutions for mobility in cities and even mobility across different geographies on the earth. So going from one part of the world to another, just the amount of technology and integration efforts that goes into making airplanes and how we travel. I think the trend that is very fascinating to watch, and that is going to impact not just education, but also actually the field of engineering, is convergence. And we see that the most simple example although it's complex, is the example that has to do with smartphones, where you now have different kinds of applications that come from so many different domains, but these are all brought together under one umbrella that allows you to basically carry out commerce, that allows you to do all kinds of other things that you otherwise would not be able to do. That's one other thing to keep in mind, the convergence and also obviously the hyper-integration issues. Now, one interesting trend that is very important for education, but also for engineering as a profession, is what I call the commoditization of skills. The commoditization of skills is important because as we look into the future, a lot of the skills that today we consider to be unique will no longer be unique because you will have engineers spread across the globe who are equipped to actually use different kinds of tools to solve problems. So with this level of commoditization of skills where you can get an engineer to solve different types of problems, it behooves engineering institutions to train and produce engineers who have unique skill sets that make them stand out. And I think that's going to be a very to watch, because we already see how manufacturing is moving around the world, and this is going to just become a trend that will really impact engineering, will force people to become much more specialized for good or bad, but we see that as something we need to pay close attention to. Another trend that I think is extremely important is the trend around computation, and basically here cognitive computing, where we're adding more and more intelligent devices. Those devices will enable us to do education in a different way, but it will enable us to also design systems that perform in a different way. So as we make computer chips smarter, we're basically having them to mimic some of the behavior of the human brain. That in and of itself will add all kinds of sophistication to how we address some of the challenges we face. And obviously with cloud computing, now that you're putting a lot of these algorithms out in the cloud where anyone can access them, it makes engineering design, engineering application much more easier to develop from different angles, but it also creates a whole set of challenges that we'll definitely have to address as we prepare engineers, both in terms of their education, but also in terms of their practicing of engineering when they leave the university. Last but not the least, which I think is fascinating and something we need to watch in terms of trends, is virtual reality, and how virtual reality creates all kinds of opportunities for engineering education as well as for engineering itself. So just 3 examples here. One shows you a group of students who are basically designing a system, and they have the ability using virtual reality to embed themselves in the design process in a way that we haven't been able to do before. This also facilitates distant collaboration, where you have engineers in different parts of the globe that can actually sort of propel themselves into this space where they can do co-design of different things. On a situation where engineers, virtual reality can allow them to basically interact in a much more sophisticated way with the device they're designing, or with the solutions they're trying to simulate or to study. So virtual reality is going to really drive, I believe, how engineering profession, but also education of engineers in the future are going to look like. So these are some of the trends I think would really help us to address some of these issues as we go forward.
So for anyone who may be just joining, we've talked about the major challenges that we face as a people and some important trends in engineering. So I think that brings us to a very important question, and that's, what ideas can you share in terms of how we can best prepare tomorrow's engineers?
Well, and that is I think where it becomes very interesting. How do we prepare tomorrow's engineers, right? And I think to do that, we have to step back and ask ourselves 3 questions. Well, not 3 questions, but one question has 3 angles to it, right? What does it mean to prepare tomorrow's engineers, right? First of all, we need to agree that we need new paradigms, right? We need new paradigms. And part of needing new paradigm is, how do you deliver engineering as a craft when you're teaching students, right? And so that brings up perhaps one of the first things to address when we talk about preparing engineers is who will deliver the education of engineers. And that begs the question is what will be the role of teachers going forward? So before we move forward, Laura, I'd like you to do a poll here just for us to explore what people think will be the role of teachers going forward in this world of hyper technology that we have around us as we go forward.
I would love to. Folks, coming up on the screen is that poll. And the question here is, intelligent machines could replace the need for teachers in the classroom. Do you agree, disagree, or maybe don't know? So it came out as 17% saying agree, 75% saying disagree, and 8% don't know. Dr. Jones, what are your thoughts there?
Well, I'm actually impressed that 70% agree with that question. I'm just wondering if we had a chance to know the background of 17%, how many of them are not teachers, and how many of the 75% who disagree are teachers. But I think, if we go back to the presentation, Laurie, and thanks for your feedback, audience. I think what is important to bear in mind here is that I believe that the role of teachers will, like everything else, evolve. It's going to have to change, right? So when we can look at the question of, how do we educate? We said we needed new paradigms. We've looked at this poll, but let's try to break this down a little bit further. So, how we educate engineers boils down to three things, right? It boils down to content, structure, and tools, right? And in all of these things, there's a role for teachers, and we'll talk about that briefly, I guess. But so the content obviously is important, the structure of how you do it, and the tools, all right? Fundamental to how we prepare engineers have to do with their curriculum, right? That's the first thing, right? And going forward, I think engineering curriculum is going to become, or has to become, by far more interdisciplinary in terms of the content. And that's just because, and we'll see that in the next couple of slides coming forward, is because the complexity of these wicked problems we talked about, some of these grand challenges, no longer can be resolved by a sole engineer who is in one space doing everything by himself. So training engineers, what they learn, the content of that curriculum has to be interdisciplinary. The teams they work on has to be also interdisciplinary, obviously, because again, remember, engineers are supposed to solve problems that we face, and so one part of being able to solve the problem will be able to understand the problems from different angles, from different dimensions. And so for this, you need to be in a group with people who have different backgrounds. Well, you yourself have to be educated from having different disciplines as part of your education, but being able to function in these interdisciplinary teams. The other thing that I think a curriculum will have to consider in terms of being in terms of change is that there will have to be a greater emphasis on experimentation as well as rapid prototyping. We have to get away from a situation where engineers design things and they actually do it on paper, but actually never get to see the product that they've designed. And so we imagine we'll have the situation where we have greater experimentation, rapid prototyping as things that are very, very important. Another aspect of the training has to be that what I call this from a library to search engine, right? From library to search engines. We now have the situation where relevant information is instantaneously available to anyone, anytime, wherever you are, once you have access to the internet, right? So that in and of itself is something that will allow us to prepare engineers in a different way, will allow them to find solutions to problems in a different way, and also decide who they work with, right? So the role of search engine is definitely one thing that we think I think will have a huge impact on how we go about doing the education. We've talked about commoditization of skills. Now let me talk about another form of commoditization which is extremely important, and that is the commoditization of education. I think with the ability of online learning, we have the capabilities today to have you learn wherever you are in the world once you have access to the modules of education that exist today. And so as we commoditize education, how will the teacher respond in this new environment where his students are dispersed across the world? So you may be a teacher in somewhere in, say, in Brazil, for example, or in Mexico, and you may have students in Africa, you may have students in China, or you may have students in Europe. So how does this idea of commoditization of education, how would that impact how teachers prepare curriculum, I think is something that definitely will impact the education of future engineers. We need to focus on big data or big information for getting new insights. Three things that are very important with regards to education. We're going to have to educate our students to understand the relevance of the data and the information they're gathering, the quality of the information, and the accuracy. Now, how do you teach these three concepts? Relevance, quality, and accuracy is something that I think we have to take into consideration as we design curriculums for the students going forward. On a broader sense, there are a number of things, skills I think will be relevant. Obviously, technical skills will continue to be important going forward, no doubt. Having analytical skills, critical thinking skills, all of these skills that we know are necessary to decision making will become more important as we move forward and have to address some of these big problems, some of these wicked problems. But there are a couple of new ones that I think we need to focus on. New in the sense that there hasn't been a lot of research, but until now is gaining a lot of traction. One is this notion of collaborative intelligence, which basically speaks to the idea of being able to think with people who think differently, right? Thinking with people who think differently. I think it's very important to bear that in mind, because as we design systems in a commoditized world of both education and commoditized skill sets, so oftentimes the perception of value of different types of issues we're facing might differ. And so how do you forge consensus on a team that is dispersed across the world? Or how do you educate students to be able to function across the world, across teams, with people who think differently but have an ultimate goal of designing something that solves global problems, whether it's climate change or other more specific problems addressing individuals? High emotional quotient is going to be more and more critical. I believe we'll have a higher penetration of women in engineering over the next couple of decades. That will bring with itself some need to transform how the interaction occurs within the engineering field, both from an educational standpoint and also from a teaching standpoint. And then obviously interpersonal communication skills. The last thing I think is important in terms of skill sets, which I cannot overemphasize, is the notion, or not the notion, is the need for entrepreneurial thinking and entrepreneurial skills. Engineers, because of the commoditization of skills, engineers are going to be entrepreneurs. They have to be entrepreneurs in their thinking. Even if you're working on a team, you have to train engineers to think as entrepreneurs if they're going to stand out in this very competitive world where skills will be commoditized and education will be commoditized. And the last thing that is important, I think, is the need to align engineering education with the emerging needs that it relates to business, to policy, and to environment. This is important because I remember myself going to engineering school. I would have summer breaks and I would go to work out in the industry, and I will see a huge gap between everything I was learning in engineering school and what I was expected to solve when I came into the real world. And so being able to align the emerging needs of those different areas, whether it's policy, environment, or business, with how you educate engineering students going forward, I think that will be very, very important.
So, Dr. Jones, your enthusiasm is infectious, and I'm almost certain I'm not alone in saying I could listen to you for hours, but I know we do have a number of questions coming into the queue, so shall we switch gears and go through some of the key takeaways before we start addressing those?
Sure, let's do that. A couple of key takeaways to sum this up. First of all, we need flexible and adaptive educational structures. And by educational structures, I include there the teaching itself, the teachers themselves, the curriculum, even to some extent how the students are sort of brought together. So we need disciplinary structures that are multifaceted, transdisciplinary, as well as interdisciplinary. This is very important because we cannot solve wicked problems, we cannot solve these grand challenges if we have outdated educational structures. And I think that's one of the things we're going to have to address going forward. We have to create more flexible and adaptive educational structures. Again, coming back to curriculum, the content is going to have to be diversified. Obviously, art, science, mathematics are very important. But I think three things that we should really incorporate in the future engineering curriculum. One is history. Engineers have to know the past to design the future. That is extremely important. The other thing is psychology. And by psychology, I include here also behavior economics, behavioral science, because engineers are building things to meet sort of a desires of individuals and to some extent even the whole society. So understanding the psychology of your customer, the psychology of the user is very important. And then future studies. Engineers have to be trained how to anticipate big things or things happening in the future. So when you design a system for today, bear in mind that it's going to have to deal with events or situations that you may not be able to anticipate, but that idea of thinking about the future should help engineers going forward. Third, the delivery mechanism have to change, tools have to improve. In this context, pedagogy has to be adaptive. We've already said that. More online learning, a greater focus on experimentation and design, and also I think a greater use of 3D printers, because I think once engineering students can see what they have conceived on paper, it will help them all in all. And then lastly, I think future engineers, as we're going to seek to tackle these grand challenges and these wicked problems, have to be more generalist as well as polymath. We need more Leonardo da Vinci's, we need more, George Washington Carver and Lady Ada Lovelace. We need people who can think across multiple engineering and non-engineering domains to address these wicked problems. So I think those would be a couple of takeaways I'll definitely want to leave with you. And so let me thank you. I look forward to your questions. Thanks for taking your time to listen to this, and I'll be happy to answer questions going forward.
Well, thank you so much, Dr. Jones. Going to give you a few moments to get a drink of water, and in the meantime, I'd like to share with everybody some resources available for you to continue discussion and continue learning more in this area. On Twitter, I've got Knovel updates and ENG Village, as well as Dr. Jones' Twitter handle right there. Certainly invited to come out to the Knovel website, as well as the Elsevier Engineering Village sites, and as well subscribe to the Knovel and Engineering Village blogs for the latest news and webinar announcements. All of this information has been put into the chat, so you have it there on your side if you want to refer to that at your convenience. It also will be included in the follow-up email that will come out early next week. Additionally, you are all invited to participate in a global academic challenge. This is live from September 28th through November 1st. And it gives instructors the chance to immerse students in practical problem-solving environment. And students compete by solving engineering and scientific problem sets online. They earn points and a chance to win prizes each week. So check that out at knowelac.com. I would like to invite Dr. Jones back to the virtual podium. Let me go ahead and start with our first question. This one coming from Roger. And he'd like to know, what barriers do you see in changing the curriculum?
Well, so there obviously there are a number of big barriers, small barriers. But if we just, in the interest of time, let me just focus on three key barriers that I think has to be addressed, right? I think the first barrier is institutional, right? The institutional barriers are there, and part of the issue here is that change is not easy. And most academic institutions have a long history, and so how do you deal with the institutional barriers? And it's not just institutional from the standpoint of the academic curriculum. It's just in terms of how people view engineering and how do they view it. Again, we saw some people said it was more science, it was more art. So I think getting the institutions to become more flexible, to getting them to move away from the old way of thinking, if you may, and don't get me wrong, it's not that the institutions are not innovative, but it's just that oftentimes the movement is very difficult. So institutional change is one thing. The other thing here, and that goes to my question about when I asked the role of teachers, instructors and teachers have to become more flexible, right? I mean, I have visited universities since I graduated myself, and when I've spoken at universities around the world, and when I have one-on-one conversations with students, the biggest complaint is that their teachers are outdated in terms of technology. Their teachers are not keeping up with the pace of change, right? And so teachers need to become much more cognizant of the fact that their students are no longer receiving information the way they received information, right? So the learning process has to change. The teachers have to adapt to the fact that they're, at the end of the day, they're there to serve the students, right? So it's like I always say, if I have a client, if I'm communicating with a client and the client is not understanding me, I can't blame the client for not being receptive. I have to find ways to adjust. So take a simple thing like experimentation, or even the way how you do your home assignment, how you engage with teachers and with students. Teachers have to be key in this change. And then lastly, I think the preparation of engineering students before they even get to the university is key here. And here I think we need to see a greater collaboration between university and high schools around a country or around the world, in terms of making sure that when the kids are in the 10th, 11th, 12th grade, you start already preparing their minds for what is to come. And so I think bridging that gap between the transition from high school to university is very important. There's more work that we can do there, making sure the teachers are flexible, because at the end of the day, the students are not only as good, but oftentimes the students will perform to a great extent in terms of the kind of instructions that they got from their teachers. Now we have to make a distinction between undergraduate education and graduate education, but I think the greater focus needs to be on undergraduate, where we really have teachers that are open-minded and willing to adapt to new technologies and new skills, which means they themselves have to modernize their skill set, right? I know a teacher at a certain university in a country who doesn't like some of these latest social media solutions, and he finds it very distracting. And I've said to him, I said, look, I understand your point of view, but that's what your students are using. So you need to find a way and incorporate some of these social media technology into how you educate your students. He said, give me one example. I said, why not create a Facebook page for the course? He said, what do you mean? I said, create a Facebook page for the course, and you will see how many students will flock to your course. And he did that, and he started to put little modules on the Facebook page, and all of a sudden, that single class attendees went up, because now students could engage in a more natural way from their perspective, right?
Absolutely. All right, let's go ahead and take a second question here. We have one from Asaruman, and Asaruman is asking, what can be done to improve the teaching and learning of engineering in developing countries that are deficient in educational infrastructures, especially practical learning tools?
This is an excellent question, and I would say this because one of the beauties of 3D printing is that 3D printing is also going to commoditize manufacturing, and it's going to commoditize learning and invention. So one of the things that can be done, especially in terms of the practical nature of engineering, right? I remember I grew up in Liberia in West Africa, and we were very great at the theory, but we didn't have all the sophisticated laboratory tools, nor did we have some of the sophisticated computing technology that exists in a developed country, right? Now, with 3D printing, with the internet, imagine what that could do to a student in a developing country who perhaps may not have access to to some of the sophisticated tools that would be needed to do production and manufacturing. 3D printing can also create the opportunity for students to experience manufacturing in a way they may never do in a normal sense. So I think we need to really focus on how can developing countries leverage information technology, all right? How can they leverage some of these emerging tools? But they're also, okay, especially in developing countries, the institutional barriers are going to be difficult to overcome, but it has to be overcome in order to improve the overall education of engineering students in those countries.
Okay, I have a question here from Natasha, and Natasha says, totally agree with what Dr. Jones has been saying. No doubt he's a Myers-Briggs NT like me. And now for the question. But how in a difficult economic climate with increasing class sizes can faculty persuade deans and et cetera to invest for the future?
Yeah, and I mean that's a very important point, because resources and resource allocation is key, right? I think one of the things that faculty can do, right, is be innovative in terms of how they interact with their deans. right? I mean, deans at the end of the day are also humans, right? So they too have to be sensitive to the times, right? And I think the best advocate for change are the students, right? And so the faculty can fight as much as you want with the dean. He may not get the necessary change you want. But if the students are aligned with the faculty, you have a very good mix right there, right? And so I really encourage teachers and professors who are advocating change to first get they and their students on the same page in terms of the change they would like to see happen. The other thing I would suggest them to do is to leverage the alumni association in schools and all over the world, because I can tell you that when I travel to my alma mater and I give a talk there, the teachers are always nervous because when I show up there, the dean is excited. The dean is always nervous because I come there and I advocate a lot of things that I know will require him to increase investments in education. But then I tell him, I said, look, if you want us to hire your students, you need to empower the teachers to give the students the education they want. At the end of the day, it's all about the messenger, right? So oftentimes I've seen cases where, professors are fighting wars with the dean of education for different reasons, and I've said to them, look, you're fighting the wrong battle. What you should do is get the alumni association on your side, get the students on your side, and let them go to war for the change you want, because there's no dean who is going to withstand the pressure or the force that's coming from a very powerful alumni association and a very powerful student body who's advocating change. So I know it's not easy, resources are tight, but trust me, I think universities, once they hear from the private sector, and that's why I think is also important, that alignment I talk about between business, policy, and environment. If a teacher can get these connections closer with the real world, I think we'll see a lot of help coming to address some of the concerns the instructors have.
All right, thank you. Okay, our next question here. Interested to know the skills required of next generation engineers, especially as everything is going digital.
Yeah, well, that's a very, very interesting question from two dimensions, right? So the digitalization of life is a reality. Actually was created by engineers, right? So engineers were the ones who, came up with the fact that we needed to go from continuous systems to more discrete systems, right? So I think I think engineering have a role to play in terms of even defining the skill sets that they need. I think as things go more and more digital, what I think is very important is that the digitalization of our lives is creating, to some extent, complex systems, right? So now everything becomes digital, everything's become integrated. And so coming back to my hyper integration theme, what I think skill sets need to be focused on is now system thinking, because what we're doing is we're actually creating systems of systems. And no longer will an engineer survive if he has a singular view of a particular device. One needs to put that device in a context. So I think systems thinking is not a new thing, it's been around for a long time, but it needs to be really reintroduced and integrated into the educational system much earlier than it is today. Now, the reason why that's important is because as we create these complex man-made systems through the digitalization of our lives, what is also happening is that we're creating a lot of vulnerabilities that need to be addressed, right? We talk about cybersecurity, which is one of the grand challenges with the National Academy of Engineering. And so engineering students need to be aware that from a systems perspective, what are the vulnerabilities? How can they anticipate the weakest links in these complex systems? I think being able to have that system thinking mentality, I think, is something every engineering student should know, right? Irrespective of whether you end up working in a singular field, you should at least embrace and understand systems thinking. And I think it should be required for all engineering students very early on that they should start having a more systems approach to the world. And there comes my last point I'll make on this is that we can learn a lot from biology and from neuroscience. And so in terms of saying what else you should learn, if I were to go back to the university, I would definitely take a solid course in biology and also in neuroscience, because there you learn very interesting things about how complex systems work because of course the brain and nature is perhaps more complex thing than we will ever have to deal with as engineers.
Fascinating. All right, I have a question here from Frank. It's actually a comment followed by kind of a multi-part question. So starting out, Frank at the Society of Engineers says he's surprised that the innovations in mobility, meaning autonomous vehicles, vehicles powered by new energy solutions, didn't make the grand challenges list. How do you think about the role of mobility technologies in our future? And do you think engineers are being trained adequately to address the delivery of new kinds of mobility? And I can repeat any of that if you like.
No, and thank you, Frank, for the question. I think to some extent, I think mobility wasn't called out specifically, but I think mobility is somewhat embedded in it. Take, for example, the redesign of urban infrastructure. One of the fundamental issues of urban infrastructure has to do with transportation, right? So how you build bridges, how you build roads, how you build overpasses, how you design cities, all of these things relate to mobility. And so I think what they did at the National Academy, where they took broad slices of challenges, because if you look at the infrastructure, it has to do with water, roads, and a whole bunch of other things. So I think mobility is definitely there. Now, the other aspect of your question is, are the engineers being trained enough to incorporate mobility in their thinking or in their training? I would say no, not to the extent I think is important. I think what has to happen, though, with regards to incorporating that is we have to find a way to make mobility almost like a course in mobility, right? Because mobility has so many different aspects, where you have mobility where you're going from point A to point B. You could even consider where you have virtual mobility, where you can sort of not physically move, but you could still move in terms of sort of virtual mobility. So I think there are many facets to mobility, but I think I agree with you. It's a field in and of itself that requires a whole new mindset, and it should be given a greater focus. I'm surprised, set aside the grand challenges, that more engineering schools haven't focused on mobility as a field and have special courses in mobility, because everything is linked to mobility, energy, right? From a transportation perspective, how you design the cars, the comfort level, congestion in cities. There are a whole lot of issues related to mobility. So I think it hopefully at the end of this webinar, some professor out there maybe decide to start a course on mobility and see. I think it would attract a lot of students, to be honest.
Okay, Lawrence, looks like we have time for one more question. So this one from James. Undergraduate students are not typically advocates of change. Grads are different. Undergrads tend to want only their AS needed by getting sample test problems with different numbers, for example. How do you get youngsters to accept creative education and be unafraid to work rather than memorize?
Well, that is a question that requires a webinar in and of itself, because I think that goes to the crux of when I talk about the transition from high school to university, right? So an undergraduate comes in with a foundation that has been set from the early start. So they've already developed a mindset in terms of how they think, how they solve problems. So I think you need to begin very early on, maybe the 10th grade, 9th grade, or even with my own daughter. I mean, she's 5 years old, and I'm already embedding in herself the idea of solving problems. It has to happen much, much earlier, because the undergraduate has already been sort of his mind has been sort of tinted to a certain extent in one way of thinking. Now, having said that, can you retrain the thinking process of an undergraduate? Yes, you can. You have to be flexible in terms of how you sort of encourage that student. And one way to do it is, I love the STEAM challenge. If there's one thing young people like, they love the challenge of working as team and creating different kinds of challenges and competitive challenges in schools, in classrooms will help. I think you need to make the education less static, more dynamic, to get young people to get involved. I don't think young people are resistant to change. I think young people are resistant to change when change is brought upon them as opposed to when they are a part of change, right? So one way to address this issue is to maybe make them part of the change. And we've seen this in all kinds of movements around the world where young people bring about the change, but they have to be part of the change. It's always difficult if the educational system is changed in terms of a top-down, where you just sort of you're mandating students to do things. There has to be a much more integrated approach where the students themselves can see value in making the change. And so I think if you do that, it becomes useful. One point I'll just make quickly, Lori, that kind of ties back to this question is how do we design laboratories in the future? I think the conventional design of a laboratory was one where you had a lot of static devices, I would call them. But I think going forward, I think every engineering class should have at least a number of 3D printers. There should be, to some extent, some virtual reality devices in those labs, and obviously there should be, as much as possible, cloud computing capabilities that will allow these students to really. It should be fun. Engineering must be fun, right? And that is the last thing I will make here. I guess we have to make engineering fun. What is surprising is that 4% of the world's population, it's an estimate, but 4% of the world's population has built the world. 4% has built the world in terms of all these structures we see. Engineers make 4% of the world, but the problems they solve actually generate trillions and trillions of dollars of wealth. Yet and still, the average person on the street doesn't view engineering in any sophisticated way unless there's a problem that has to be solved. So I think we need to embrace engineering and see us as engineers as the ones who have built the world, and we will transform the future. And I know this will sound challenging to some of my colleagues who are in liberal arts and law and the field of law and business, but at the end of the day, we as engineers, we make things and we fix and solve problems to make people's lives better. And I think that is something we should embrace. And if we do that, we would win the sort of the PR war in terms of which is the most attractive field to enter: engineering or law, engineering or media. I think engineering is and must remain the most attractive field, but we as engineers must take the time to advocate for that the best we can.
Okay, thank you. And on to our next question. And Frank's asking, how should a future engineering lab look?
I think a future engineering lab has to be designed from three angles. First of all, it has to be designed for the students to learn how to go from conception of ideas to actual production and actual manufacturing of it. So that means I would like to see more 3D printers in future engineering labs, because again, just designing things that you can't actually see the outcome of, I think doesn't give students that inspiration. It's always great to see the outcome of your work, and 3D printing will help. I think engineering labs going forward should also have a very strong focus on virtual reality, because again, virtual reality, it does something with your thinking that you can actually immerse yourself into the problem space in a way that is different. The idea that you're using many more senses when you're in this virtual world is something that I think will really accelerate the ability of engineers in the future to make better decisions and to also see the problem space from multiple dimensions. Because when you're in that 3D world, that virtual world, it does something to the brain that I think we're only beginning to scratch the surface. So I think having more virtual reality technology types in that. And the last thing, as we've had in the past, in the old days, you had your slide rule, you had your calculator, and then you had your computer. I see going forward, big data and cognitive computing coming the new microscope of the future, because now you can actually get so much data, and with that data and with the right analytical capability, the right computational skills, you can get all kinds of insights. And so back in the day, we used microscopes to understand physical world. I think we're going to use big data and computational analysis to gain insights about man-made world of complexity. When we bring all these complex systems together, when we collect the data and combine data, but the physical world with data, the man-made world, there is no way to address improve our understanding if you don't use some of these advanced computational techniques. And I think those are the three new things we should have more of in laboratories going forward.
Okay, thank you. Edelson's asking, how do we lure women into engineering?
Well, first of all, if you remember my last slide when I talked about polymath, there have been a lot of engineers who were women. There have been a lot of polymath back in history that were women. If you take Lady Ada Lovelace, it's only recently that people were able to acknowledge that she was, she's been now seen as the one who wrote the first computer programming that we know today, right? So I think one way to lure more women to engineering is to talk about women in engineering who are making significant strides. And that is something we have to make a concerted effort to lift up the contribution of women in the past, right, as role models for women going forward. And we shouldn't be shy in doing that. The fact of the matter is I have worked on many multidisciplinary teams around the world. I've worked on teams in Europe. I've worked on teams in Africa and Asia, in the US. And for me, it's clear that there's something to get out of bringing these groups together, and so I think you get more women in engineering when you raise the profile of women who are there. I think also what we need to do is that history needs to be revisited. That's what I said. Engineering education should include a stronger dose of history. And part of what I think a good curriculum in engineering should go back and research and bring to life what are the contributions that women have made to engineering over decades. I think when you begin to do that, then you will see the role of women becoming even more obvious to us going forward.
Okay. Michael's asking, what role does industry play in educating future engineers? For example, cooperative education and work integrated learning programs.
I think the role industry plays is extremely important. So one of the things that I know from my own education when I was going to university, I went to school in Sweden, and one of the things that was very, very interesting there was that much of the research I did and when I was in engineering school had a very strong industrial dimension to it. And so I would part of the requirement actually was to do 17 weeks of practical training, as it was called back then. And that training meant that we would actually go out in the industry. I remember one of my first practical training was to work in a cable manufacturing a plant that was producing underwater cable, right? Were back there, so that gave me a lot of insights into how machines work and all of that. So I think industry has a very important role to play. Industry has also an important role to play in terms of trying to map out what they see are the problems and challenges they would like engineers to solve. There is one gap I think that needs to be closed, is that oftentimes when engineering schools come up with their academic plans, there's a very there's not as much input from the private sector or from the industry as I think there should be. And so I think by integrating engineering problems, real world engineering problems into the curriculum, I think it would help for us to get this relationship between industry and academia to become much more cohesive going forward.
Okay, I have a question here from the student perspective, and that is, as a student, what recommendations do you have for me in terms of preparing for a career in engineering?
Well, first of all, I think in preparation for a career in engineering, you must bring your passion for solving problems, right? Part of the preparation has to be that you have to be prepared to perhaps be the lone wolf in a world where engineers were only 4% of engineers in the world. And for the entire world population, only 4% of us are engineers, but yet and still we pretty much build the world. So I think in preparation, you need to focus on your problem-solving capability. You need to focus on the fact that you have to have a much more diversified portfolio. You need to also be curious, right? Curiosity is something that I think really helps a young engineer to be successful going forward. And so some of the things that I tell people all the time is, most of the magazines I used to read in engineering school had nothing to do with electrical engineering, which was my specialty. I used to read things on biology. I used to read magazines on psychology, just because of the curiosity. And I think that is something that, you can't force people to be curious, but you can emphasize the need for curiosity. So I will tell every young engineer that to be successful in your curriculum or in your education, you have to be curious of things around you, but then you also have to be patient in terms of looking for solutions, because one of the challenges that I think we all face is that we're rushing to find solutions to complex problems, when in fact part of the real challenge is the patience of trying again. And then lastly, I would say, focus on, having a systems approach to things. Don't just look at things from one perspective. Try to develop the ability to look at things from multiple angles and ask questions. One of the things I always tell people who I mentor a couple of engineering students around the world, and I always tell them that you have to be curious, but you also have to ask questions. And that is one thing that's important. The more questions you can ask as an engineer or as an engineering student, the better prepared you will be. Because before you even do the first design, you should have asked all the possible questions. And the actual design and manufacturing should actually take maybe only 10 minutes of the time, right? The remaining 10% of the time, the remaining 90% of the time should actually be spent thinking about the problem, asking many questions about it. And once you've done that well, the actual design and the engineering will be much more easier to do.
Okay, I have a question here from Bing Yu, and that is how to equip the engineering education with the state-of-the-art information when they themselves do not work in the engineering industry.
Well, I think one of the challenges here is that universities for a long time have been designed in silos, right? You have different departments, and these departments operate in silos. And so what happens is when people graduate from these universities, they've been trained to live in silos, and then when they get out into the private sector, they continue to live in silos, right? So I think one way of equipping the educators with the latest technology is to actually create more opportunities for engagement, right? So, for example, this webinar we're having is one very interesting way where you can have webinars that bring together folks from multiple disciplines and have them to start the dialogue. As long as we remain in our silos, you will not be able to breach this gap in terms of being exposed to information technology. So I think the more we can create opportunities for engaging on a multidisciplinary level, I think the better chances we'll have to achieve the goal of bringing information technology to educators and having them embrace it and not feel threatened by using it.
Okay, question here from Joe. What role do you envisage for librarians in the education of engineers?
Joe just asked a very interesting question that goes back to me saying from library to search engines. Joe, I remembered when I was doing in my undergrad or my engineering courses in Sweden. One of the courses we had to do was information search. We had to go into the library and find information. I remember I was meeting the librarian, and they will help us and show us how to use all these different systems for searching, right? Today I can search 10 times faster by sitting at home in front of my computer, right? So the role of the role of librarians, they have to go from being librarians to provider of solutions that will help make information search more valuable from the standpoint of relevance, accuracy, and even being able to help people find the right information. Because here's the thing: just because you have access to the internet, just because you search and find a report, doesn't mean that report in and of itself is accurate, right? So part of the role of librarians have to go from just helping us to find information or to find a book to be more subject specific, but to also have some depth. So just as we're asking the educators to retrain themselves, we're going to also have to ask the librarians to retrain themselves, right? So they're going to have to get more in-depth understanding of the fields within which they are providing, search support. Right, so I see librarians as a search support staff going forward, where they will help you to search what you're looking for in a much more different way. And I think that's something we'll see happening with these more sophisticated search engines. But the engines are just a tool towards a means to an end. What is still important is how do you take all these different search queries that you're going to do to find the right information quickly, right? And so I think there's still a role for librarians, but they have to change.
Okay, I have a question here. Would you elaborate on adapting online education and engineering? And at the same time, we must apply hands-on education and practical education in labs and pilot plants?
I think both these two concepts go hand in hand. And this is why I say, right? Again, remember, one of the reasons we're going to have to adapt the engineering profession in terms of educating our future engineers is because the recipients of this education, they themselves have changed how they receive information, right? And so today, most of what most students do, they do it online, or they do it using handheld devices, or they do it using some form of a digital device, right? So you can decide to stick to the old way of how you deliver knowledge, but if you do that, you will not get the students. So first of all, just educating them on, say, basic physics or mechanics, right? How you do that, how you come up with innovative ways to address those issues, means you still have to have that ability for them to use online where it's useful. Give you another quick example: Facebook. A professor I know in mechanics who was having difficulty attracting students to his course. And we were talking, I said, look, create a Facebook page for the course. And he said, why? I said, because most of your students, that's where they go to interact. They interact on Facebook. And he thought it was kind of a joke. He did it, and he saw a surge in the number of students participating in the course. Now, you have to combine that with the practical dimension of engineering. So you do all these nice things using online learning, exchanging of ideas. Then you take that information and then you go to your 3D printer and you actually productize the ideas, the concepts which you've studied. You can take those ideas and go to your cognitive computer system you have at home, and it can allow you to get greater insights in the complex systems you have to deal with. So I think they go hand in hand. Both have to change. The tools have to be adopted. The content and delivery also have to be adopted.
Okay, Lawrence, I think this is going to be the last question we have time for today, and that question is, what can be done to improve the teaching and learning of engineering in developing countries that are deficient in educational infrastructures, especially practical learning tools?
I think one of the beauties of 3D printing, and by the way, for full disclosure, I am not a manufacturer of 3D printers, and I absolutely do not have investments or shares in a 3D printing company that I know of. So I'm not trying to overemphasize 3D printing. I have just seen the fascinating results of using 3D printer within an educational environment. And think about this, right? You're in a laboratory, or you're in a school, in a village somewhere in the world where you have all the theoretical skills, but you cannot use your imagination beyond theory because you don't have the ability to test these things and see them in actual, in its form. So in developing countries today, with broadband capabilities, you have the information technology access. So in terms of getting the theory, I think we have enough online tools to get enough theory dispersed across the world because of broadband communications and all the work being done on communication systems, right? In fact, in Africa, for example, the fastest growing population of using mobile technology is in Africa, right? So you can use mobile technology to train on the theory. But how do you get the practical? Well, there's where you have things like 3D printer, as the price go down, become more available to different parts of the world where you have developing issues there. Another thing is, if you look at the role of major organizations, the multilateral banks like the World Bank, United Nations, the Gates Foundation, all these different organizations, both philanthropic as well as private, are beginning to move towards this idea of bringing different tools to developing countries to help nurture the ability to not just be theoreticians, if you want to call them, but to also be practical. One simple example I'll give you to wrap this up here is, as Laurie said at the outset, I'm the co-founder of an organization called the Center for Sustainable Development in Africa. One of the things we're about to launch pretty soon here is we're about to launch a campaign called 30 by 30, which is a campaign to get 30 million kids in sub-Saharan Africa to learn to play the game of chess. Now, you ask yourself, why is that important? Well, that is important because chess allows you to develop a lot of cognitive skills that will open their imagination of these kids to have them to begin doing all kinds of things. Well, we're not only stopping with the chess, we actually are partnering with a company that is designing 3D printing. I'm not going to call the company's name to not do commercial yet, but designing 3D printers. So we're bringing together the ability to not just to train these students in their cognitive critical thinking skills, but also allowing them to be able to use 3D printers to be able to start to make things. And so I think going forward, in terms of the developing world, we need to provide not just tools that allow them to accelerate the learning of theories, but we also need to give them tools and technology that will allow them to improve and develop their ability to make things, because engineers make things, and I think much of the problems in the developing world can be solved when people start to locally make things in those parts of the world.
Well, Dr. Jones, before we close up, I just wanted to give you an opportunity to leave us with any last or any final comments.
Well, my last comment today will be this, right? Engineers, we make up 4% of the world's population. We have built the world. As we look around, you see that without engineers, most of the advancements we've made as a human species would not have happened. Unfortunately, as engineers, we've taken a backseat and we haven't gone forward to really make our voices heard. And so I would challenge anyone listening to this, any engineering professor, any student out there, to be proud for being an engineer, in that we as engineers design solutions to solve problems. So by the year 2020, 2030, 2050, it is engineering that will provide the necessary solutions to tackle some of the biggest problems in the world. And we need to find a way to get an acknowledgement from the rest of society that the 4% of the world who's designing these solutions need to get the recognition that without them, the world will not be the place we want it to be in the decades ahead.
Well, very well put, and thank you. And folks, we are just about at the top of the hour, and there were so many great questions. If we didn't get to yours, you can expect an answer over the next 2 weeks. Before we sign off, I'd like to thank each of you for joining us and trust you found today's webinar to be of value. Of course, special thanks to Dr. Lawrence Jones, as well as our sponsor, Elsevier. I'd also like a special shout out to our logistics producer, Terry Holland, for her behind-the-scenes collaboration and support. Most importantly, thank you all for joining us. And as your moderator, this is Lori Dearman saying, have a great rest of the week. Bye for now.